Thank you to our first three morning speakers for their wonderful discussion. And now we're moving on to the second half of the morning, so it's my pleasure to invite to the stage Randy Giles.
Gosh, what a privilege to stand at this stage today. Sure wish I was giving a talk, Marcus, but I'm not. You know, maybe the bicentennial. But what if I instead stand here in complete silence for a minute? No information, zero channel capacity. Now, wouldn't that be something at the Shannon celebration? But that's actually not why I'm here. It's my delight, rather, to introduce our next speaker, Professor Olgica Milenkovic. Professor Milenkovic is a professor at the University of Illinois Urbana-Champaign at the Coordinated Sciences Research Lab. She is an NSF Career Award winner. She had received the DARPA Young Faculty Researcher Award. She has received the Dean's Award from the university and received many Best Paper Awards. And most importantly, she had been a consultant to Bell Labs in 2005 and 2006. Now I could actually talk about her research interests, and you'll find them here in this book, and you'll find them in my notes here. But after discussing with her this morning, these are totally inaccurate. Her real passion is coding in synthetic biology, and her other passion is compressive sensing, theory and practice. Please warmly welcome Professor Milenkovic.
Randy forgot to mention that my biggest passion are my cats, but this much information I really didn't disclose. So I'm really flattered and glad to be here and to celebrate Shannon and Bell Labs together with Shannon, not just with this event, but in my talk as well. And the talk that is dedicated to a topic that brought together many different disciplines and areas for a good period of 10 years of intensive research, which we now call compressive sampling or compressive sensing. And without further delays, let me start with the same picture that we saw in, yeah, exactly, in Vince Poor's talk. We both probably borrowed it from a nice online source, which we don't want to disclose. And the paper that Shannon wrote in 1949, where he basically stated and proved the sampling theorem. And the sampling theorem, as we know it, and we use it in communication engineering ever since. And literally what Shannon did is he stated a very straightforward theorem. It was Theorem 13. If you believe in the Mayan calendar, that was a very bad number to assign to your sampling theorem. But if you are Italian, then it should be a lucky number. And if you're an information theorist, equally lucky number. So he just stated something we all now know so well, that if you have a signal ft that contains no frequencies over w, then you can represent the signal with an infinite series that involves sinc functions and samples of that signal. So clearly, there were some mathematical missing holes here. You would probably now say that f is absolutely integrable. You would try to say that, yes, this is an infinite series, so this formula should be taken in the L2 sense. But this is a simple and nice result that all of us can appreciate and understand. So what Shannon also did is he commented on this theorem. He said that this is a fact, and I'm quoting him, this is a fact which is common knowledge in the communication art, implying that applications of this theorem were present at that time already. But in spite of its evident importance, it seems to not have appeared explicitly in the literature of communication theory. And if you look at this statement, you see that Shannon pretty much knew a lot of history, because yes, this was used in communication theory, and from what I could see, the earliest use of the sampling theorem goes back to a patent by Miner in 1903. And I tried to get a better quality picture, but apparently it was impossible to recover it from the internet. And he was using this sampling theorem in an experimental fashion. He was trying to demonstrate time division multiplexing for telephone signals. And he wrote a very nice long explanation how he figured out what is a good sampling rate to use. And at the same time, not in communication theory, but in mathematics, almost 30, 40 years before Miner's patent, there was a flurry of interest, and probably 50 years, there was a flurry of interests in mathematics regarding theorems and results that are closely related to the sampling theorem. And I have to say, I grew up in former Yugoslavia, and when we talk about the sampling theorem, we usually mention, believe it or not, Cauchy and Kotelnikov. I mean, we clearly have to pay our tribute to Kotelnikov, but Cauchy was a little bit surprising, but if you dig out some of his papers, you would see that he was talking at that time 160, 70 years ago about non-uniform sampling techniques in a way that can be only deciphered if you know what you're looking for in the text. So to continue along the lines of the tribute to Bell Labs and Shannon in particular, it was a great pleasure when I was a consultant here at Bell Labs to meet Henry, and I don't know if he's in the audience, Henry Landau, and to spend a lot of time talking to him and checking New York out as well a little bit. And it was equally a big delight to read his paper, which was entitled Necessary Density Conditions for Sampling and Interpolation of Entire Functions. Henry did some outstanding work on extending the results by Shannon and all these mathematicians that contributed to this area by looking at multi-band signal, non-baseband signals, basically non-uniform sampling. And he stated a result, which I'm only citing in a vague way to avoid the use of too much mathematics here, that you can still do sampling a la Shannon, and the way he described it, the theorem is now sometimes also known as Shannon-Landau sampling theorem, if you have signals that are multi-band bandwidth signals. So for example, here, all these three signals have the same effective bandwidth, but they're spread out in different ways, and sampling in the classical way would really be wasteful. And Henry was talking about stable sampling, about conditions for stable sampling, and what kind of sampling rates do you need for these conventional signals that have multiple bandwidths. And then he also talked about another Bell Labs researcher whose work may not have been that well known. So Henry's paper came out in 1967, and Ben Logan's paper, I believe, came out 2 years earlier. And Ben Logan is now acknowledged as one of the people that really inspired and sparked the field of compressive sensing, as you will see a little bit later. His work was related to developing a theory for corrupted band-limited or multi-band signals. So Ben Logan, or Ben Tex Logan, was looking at the problem of trying to find a good way to reconstruct a signal which is corrupted. And to use this, he used something that in compressive sensing now goes under the name of L1 reconstruction. So where else was this work or this line of work used? So again, people were working on an area that Shlomo was mentioning a lot way before compressive sensing came about. And one of my favorite results in this area that is called approximation theory relates to the part that connects with sampling theory. And the question of interest there is, what if we only care to sample so that we approximate the signal? And this was an area of research that no discipline left untouched. And again, to balance the Eastern and Western bloc, my favorite results, let me start with the Eastern bloc, was the work by Gelfand and Kolmogorov regarding their widths. And there is a formula here that you don't even have to try to interpret. Let's think of Kolmogorov's widths as some way to try to see how well you can approximate a set by using a linear subspace. And the way you do it, you check all linear you fix a subspace, linear subspace of dimension m. You see what is the worst approximable point by that linear subspace. And then you try to find the infimum over all possible linear subspaces of dimension m, and that is what is called the Kolmogorov width. The Gelfand width is something that deals with projections, has a very similar interpretation, and there are a lot of interesting duality results for Gelfand and Kolmogorov widths. And in the computer science and machine learning theory community, in parallel, there was this great development that resulted in a result that is called a lemma, and which should have been a theorem, probably even more than that, the infamous Johnson-Lindenstrauss lemma. And it really set the stage for many interesting results in compressive sensing. It just talked about having a set of points in a larger dimensional space and how to embed those points in a smaller dimensional space by using the fact that there exists a specific Lipschitz function that preserves the distances between these points. So with all this work and all these results that were basically accumulating for more than 100 of years in various disciplines, it really came as no surprise that suddenly, maybe 10, 15 years, more, now we're in 2016, 20 years ago, people started thinking of a new type of sampling, which is called or known as compressive sensing or compressive sampling. And it really united all these ideas that I talked about in a very unique and interesting fashion. And the work nowadays is attributed to Donahoe at one side, Candace, Romberg, and Tao on the other side. And it basically said, can we do sampling and compression at the same point? Donahoe's statement was, why would we sample if you're later on with a very high rate, if you later on can or have to reject most of it. And the key guiding property of the signals that people were interested in were sparsity. And this diagram that we see here is something you see in every paper on compressive sensing. It just says you have a sparse signal, let's say a k-sparse signal, dimension n, where k is much smaller than n. Can you do some form of measurement or sampling of this signal so that you get very few measurements, but you still will be in the end able to reconstruct the signal either with some approximation error or with some other guarantees, and use this in practical systems as well. And as I already mentioned, this theory and these results are really building on a combination of all the things we heard before, sampling theory, information theory, computer science, because people were working on streaming and sketching algorithms before compressive sensing came along, dimensionality reduction and other techniques. But there was also this circular exchange of ideas, because this is what inspired compressive sensing. But then to address many challenges in compressive sensing, we went back to these tools. We went back to information theory, computer science, coding theory, and we tried to resolve some of these issues. So compressive sensing has a very strong connection to other areas of information and coding theory. So one thing that we know now as Boolean compressive sensing is actually group testing, has been known since World War II, when Dorfman was trying to test soldiers for the presence of some rather unpleasant bacteria and viruses, which we are not going to disclose. And Dorfman was doing what is called blood pooling. And the idea was, why don't we combine blood samples and do just one test for multiple soldiers? And it didn't work, because you're diluting the blood too much when you're pooling. And so people forgot about it, but coding theorists liked the idea a lot because it involved a lot of combinatorial thinking, and they pursued it. And the idea is pretty much the same. If you know that not too many, hopefully, not too many soldiers are infected, then you should be able to get away with very few combined or combinatorial pools to identify who the defectives, as they call them in group theory, are. Then there is this connection of compressive sensing to the area of low-rank matrix completion, where you're basically looking at exploring sparsity and sampling in some untraditional domains. So you don't try to deal with sparsity in the spectral domain or in a specific basis. You're just looking, let's say, at matrices and at their eigenvalues and how many of these eigenvalues are effectively non-zero. So what is interesting is this line of work, which is very closely related to compressive sensing, got a lot of interest in the moviegoer community because Netflix was putting up a challenge for good recommender system design and beating a certain threshold for recommender system design. And again, here in this area, people won the Netflix challenge. They basically were probably the last people or first people to win this prize after the fact that privacy concerns came up, and after it was realized that recommender systems can leak information about privacy, the Netflix challenge was abandoned. So we don't have it anymore. And one interesting thing that I really like about this observation is if you read the paper by Shmatikov and his student, this is the paper that basically showed how to crack the Netflix, how to invade Netflix privacy. They used Berlekamp-Messi decoding. And if you look at the paper entitled Local Privacy, you will see how they try to explain to their readership what the Berlekamp-Messi algorithm is. So much about algebraic coding theory not popping out in every aspect of life, even when it comes to privacy. So, and there were a lot of other interesting directions in physics that I'll skip for the sake of time. And what are the key questions that people try to address in compressive sensing? So the key questions were really the questions we had in classical sampling theory. Shall we do deterministic or random sampling? And there are those of us that believe in deterministic sampling, those of us that believe in random sampling. If we want to do deterministic or some kind of combinatorial sampling, come up with nice-looking mathematical, number-theoretic, or combinatorial formulas, then what we have to do was basically look at the properties that would allow you stable and controlled error reconstruction, basically. And if you look at or go through the literature of compressing sensing, you will see words or terms like spark, null space property, restricted isometry property, also affectionately known as rest in peace, you're going to be fine with reconstruction. But for example, spark, when I first saw spark, I said, but this is a coding theoretic concept. Why are you calling it spark? It came from the from the signal processing community. The null space property was an interesting property which was developed by Shu and Hasibi. And Hasibi, I believe, was here for many years before he moved to Caltech. So these properties were used, they were formulated and used to construct good sampling matrices. And this is where the algebraic coding theory came back, resurrected. It just doesn't want to go away, because once these properties were established as properties that guarantee some form of reconstructibility of the signals, great people like Rob Calderbank, who I respect a lot, quickly used Reed-Miller codes to construct nice sampling matrices with very interesting properties. Before that, Gilbert and Tropp used BCH-like constructions for their sampling matrices. We used LDPC codes, specially coupled codes were used later on. And the key properties, which is very interesting, and it really ties well to one of the best, student talks yesterday, is that the distance spectrum, higher weights, and exit charts played a very similar role in trying to establish some fundamental properties of these matrices and their performance in compressive sampling. So about another burning issue and an important question was, you know, we have some ideas how to sample, but how would we reconstruct the signal? So there were a lot of different approaches, but the one that was really the approach that captured the imagination of the community was L1 minimization. And it basically says, try to find a signal, and this is a really quick and vague description, try to find a signal that agrees with your measurement and has the smallest L1 norm. And what is very interesting is this is exactly what Logan was proposing in Bell Labs in the 1960s. And Donahoe gives him a lot of credit in his work for really establishing this concept and this idea for use in future use in compressive sensing. But then that's not where it stopped. For example, a large number of greedy algorithms came about, and I will comment on one algorithm that was done in my group. We were looking at papers about A-star decoding. It was a nice and old idea that was pursued by Hahn and later on by Fossoyeur. And he says, oh, this decoding method seems to be a really good idea to try to implement and use in compressive sensing as well. And we named it Subspace Pursuit, only to realize later that there were at least 5 other subspace pursuit algorithms out there. But nevertheless, there were other algorithms like approximate message passing, which is a beautiful algorithm that uses belief propagation ideas by Donahoe, Malecki, Montanari, and other algorithms that are building really on the theory of decoding and using it in an intelligent and inspired manner. So this was a really quick overview of what do we know about the history of compressive sensing and what were the challenges and where did information theory and coding theory come into the picture. But given that the topic was of such interest to a broader community, not just the theoretically inclined researchers, it quickly found practical applications in many areas. Analog digital conversion, that is obviously one area where you would use it. But then one of my favorite topics was MRI imaging. Lustig, who is now at Stanford, was pioneering the use of compressive sensing techniques for imaging technologies. Liang and Bressler, 2 of my colleagues, did some exciting work in that area as well. Single pixel camera, I'm pretty sure you have heard about it. Topics you may not have heard are remote sensing and network tomography, recommender systems. But then the last, because it's usually the one that makes people feel a little bit uneasy, bioinformatics and biology. And there was really no hocus pocus voodoo magic in terms of using compressive sensing in these areas, because these compressive sensing was used to design experiments. And people in this area were not trying to build a new theory. They were trying to use combinatorial methods, coding theoretic methods, to perform their experiments. And one such experiment, probably the first along these lines, was done by Yaniv Ehrlich, who is now at Columbia University. And his research, he called it DNA Sudoku, ended up on the cover page of the Nuclear Acid Magazine journal, which is one of the best journals in the area. And not to be outdone with that line of work, I figured that the best way to end this talk is to put slides that may look cryptic, one slide that may look cryptic, but it's probably the dearest slide of my research career. It's my first wet lab experiment. It's a DNA compressive sensing microarray, which I did basically depleting my startup package when I went to Urbana in 2007, asking everyone to give me extra funding to just complete and do this. And I remember my experience walking into a wet lab and observing a large amount of ice and telling my postdoc, Wei Dai at that time, wow, it seems like biologists like their drinks really cold. And there were buckets and buckets of ice. And then I think $20,000, $30,000 later, we realized, no, the ice is there to keep your DNA samples cool, which we didn't know. We put it in bright daylight. And there goes a $20,000 check. And what we did is we tried to implement, basically do a tribute to the area of coding theory by implementing a sensing array that uses a Hamming code. And so what we did, this was the first experiment, we made it ourselves, we tried everything, and we succeeded, is to have 3 sensors, 3 dots, or spots, which are equipped, or each of these spots contains DNA that acts like a sticky tape, which can stick to very particular strands of bacteria. And we had 3 spots and 7 bacteria. So you see why hemming came about. And we wanted to do the encoding in such a way that we are able to read exactly the binary encoding of the bacteria that was present in the sample. So we could clearly identify 1 bacteria out of 7, but we only used 3 sensors or 3 spots. And so, for example, oops, this was not what I intended to press, but that's fine. So this one would say, this screenshot would say, you have bacteria 1 present. This screenshot would say you have bacteria 2 present. And this one here would say you have bacteria, let me do the math, 5 present. So you could read exactly the identity of the bacteria through this combinatorial encoding. And the key to success was really, yes, paying a lot of money, unfortunately, spending a lot of time in the lab, unfortunately, but also using coding theory. So we went back to something that people have forgotten at that time called Euclidean superimposed codes. We developed our own coding compressive sensing hybrid, which was called integer compressive sensing. In the process, we also had to look into quantized compressive sensing, because the problem with the DNA sensors or spots is the fact that they saturate. You do this signal readout by observing light intensity, and at some point, because most probes are already hybridized, you don't get to see any further increases with the concentration of the substrate, so you get to something that looks like a quantized version of compressive sensing. And then we had to come up with models, and this is a line of work that is now called as model-based compressed sensing, which was really developed by, in great detail by Volkan Chefher and Richard Baranyuk in a series of papers. So this was basically what you would call a project that needed adult supervision, but made us all happy because we managed to bring together DNA and hemming. And the hope is that we will not stop trying to find exciting applications for coding theory. I am a coding theorist, I'm not an information theorist, but I can tell you that the excitement for coding theory in experimental design and in synthetic biology is exceptional. Just before coming here, I was at Washington, D.C., attending a huge panel and meeting of all the major players in synthetic biology, with the goal of establishing a new field where we can do basically DNA computing, DNA storage. And 3 topics were discussed, 3 topics that were deemed as very important: DNA synthesis, DNA sequencing, and coding. And with that, as a coding theorist, I would like to thank you all for being here and the organizers again for the invitation. And I'm ending with a tribute to Claude Shannon and all the other great researchers that made sampling theory and compressive sensing happen. Thank you.
What a wonderful talk, Olgica. Thank you so much. So now, are there any questions? Marcus, please.
So I'm going to try and get the answer from you that my researchers have been unable to give me. Randy snorts. Yeah. Do you think there will be object or tasks-specific sampling matrices or codes? For example, for voice samples, for edge analysis of moving things versus static things. Will there be classes of things that are a little bit application-specific?
Oh, yes.
Like that? Because, as we, again, my theory about if we're sampling all these images and voices, and maybe it's infrared images or ultraviolet images, they're going to have different properties we're looking for, whether it's edges or whether it's thermal images of things or people. And I suspect there's a new class of things there that are very efficient at that type of analysis. Do you think that's true?
No, so it is actually true, because very often if you have an application, you cannot choose your sampling matrix. It's given to you by the problem. And the question now becomes, first there is the theoretical question, can you even do something with this sampling matrix? What can you, how large does your system have to be in order to use that sampling matrix? And for example, the DNA microarray experiment, because all our observations are counts or concentrations, which are positive, we basically developed a new framework which we call integer compressive sampling, where you are dealing with signals which you know are integers, have integer coordinates, and then that was basically Euclidean superimposed codes. And there were a lot of extensions between that allowed you to do a lot of nice combining of coding theory and sampling theory. So basically, it really depends on our application. If you talk to MRI people, they would tell you, oh, our signals are sparse in 2 different bases. How do we exploit that? If you have a nice application, there will be always nice theoretical questions to ask. And at the end, nice rewards with the practical implementation as well.
All right, for the economy of time, we'll finish here. Let's thank Olgica one more time.